At the outset, there existed an incredibly dense mass of matter. This mass underwent an event that led to the formation of the particles, stars, and galaxies we observe today. For many years, this explanation has been upheld by physicists. However, recent research has introduced a new perspective, suggesting that the universe may not have the early beginning that was previously accepted. Instead, it could be part of a cyclical process where the universe undergoes a series of expansions and contractions, potentially in a repeating cycle. Brian Cox, a prominent physicist, has raised questions about the traditional Big Bang theory, arguing that something cannot emerge from nothing. This line of inquiry adds an intriguing dimension to the discussion. Additionally, findings from the James Webb Space Telescope have revealed data that challenges the notion that the Big Bang marked the universe's definitive beginning. This raises a critical question. If the Big Bang was not the start of the universe, then what was? Join us as we explore the origins of the universe, delving into the implications of the Big Bang theory. If you're eager to stay updated on cosmic discoveries and theories, consider subscribing to our channel, liking this video, sharing it to reach a wider audience, and activating notifications. Scientists have developed a detailed understanding of the universe's early stages, known as the Big Bang theory. According to this model, the universe was once much smaller, hotter, and denser than it is today, approximately 13.8 billion years ago. During this period, all the fundamental particles that compose our existence were created within minutes. In this scenario, our universe, including stars and galaxies, was once condensed to the size of a peach, with an astonishing temperature exceeding a quadrillion degrees. Interestingly, this remarkable narrative is continually evolving as new observations are made. Astronomers have studied everything from the remnant electromagnetic radiation of the early universe to the abundance of the lightest elements, finding consistent support for the predictions of the Big Bang theory. To the best of our knowledge, this depiction aligns perfectly with the reality of our universe. However, despite its strong explanatory power, the Big Bang theory does not provide a complete picture. There remains an unresolved aspect of this question: our understanding of the universe's initial conditions. This gap arises largely due to the limitations of our current theories. The combination of general relativity and high-energy particle physics offers a significant theoretical framework, but as we probe deeper into the fundamental aspects of the universe, the mathematical complexity increases dramatically, leading to challenges where our existing methods fail to provide substantial solutions. One indication of this complexity is the concept of a singularity, an infinitely dense point at the beginning of the Big Bang. This notion suggests that the universe was once compressed into an incredibly tiny and dense state, which seems implausible. To address this challenge, we need to explore new frontiers in physics and develop approaches that transcend these limitations, offering a more comprehensive understanding of the universe's origins. Our current tools and theoretical frameworks are insufficient to tackle this challenge, prompting the need for new physics that can integrate gravity with the other fundamental forces at extremely high energies. This is where string theory comes into play. String theory aims to provide a coherent model that unifies gravity with other fundamental forces, particularly at super high energies. Essentially, string theory posits that it can explain the fundamental characteristics of the universe. Within string theory emerges the concept of an aeon, derived from the Greek word meaning age or era. This idea suggests that the Big Bang we know may have been the result of a prior event, implying that it was not truly the beginning but rather part of a continuous process. The possibility of an aeonic universe has led to the development of a related theory known as cyclic cosmology. While the idea of a cyclic universe has been contemplated for centuries, string theory provides a robust foundation for this concept. In the framework of cyclic cosmology, the universe behaves like it is perpetually oscillating between massive expansions and contractions in a never-ending cycle. During the inflationary epoch, the idea of the multiverse remains largely speculative, but it presents intriguing possibilities for addressing calibration issues in cosmology. One of the prominent challenges in this field is the apparent improbability that the fundamental constants of nature are perfectly tuned to allow for the existence of complex structures like galaxies, stars, and life itself. Another compelling notion that questions traditional concepts of cosmic beginnings is timeless inflation, a theory proposed within the framework of inflationary cosmology. Timeless inflation suggests that the universe undergoes an infinite series of inflationary phases, each resulting in new regions of spacetime with potentially different physical laws. In this view, our observable universe is just one of countless regions within an eternally expanding infinite foam. This concept prompts significant inquiries regarding the nature of time and causality in the multiverse. If inflationary bubbles continually spawn new universes, the idea of a singular beginning or ultimate origin becomes increasingly elusive. Instead, the universe appears as a dynamic, evolving entity embedded within a grander cosmic tapestry of inflationary growth. Recent advances in theoretical physics have sparked interest in alternative cosmological models that challenge the conventional narrative of big beginnings. For instance, some researchers have explored the concept of a cyclic universe, where the Big Bang is not a unique event but rather one phase in an endless cycle of cosmic expansion and contraction. According to cyclic cosmology, the universe experiences successive cycles of creation, growth, and destruction, each concluding with a big crunch followed by another Big Bang. This theory draws inspiration from ancient cosmological ideas and modern theoretical frameworks, such as string theory. Within the context of string theory, which posits that fundamental particles are not point-like but rather tiny vibrating strings of energy, the notion of a cyclic universe emerges naturally from certain interpretations of the theory. String theory suggests that the universe may exist in higher dimensional spacetime, where patterns of expansion and contraction are the result of interactions between fundamental forces. While the cyclic universe theory remains speculative and faces significant challenges in terms of observational evidence and theoretical consistency, it represents a bold attempt to reconcile quantum mechanics with general relativity on cosmological scales. By proposing a continuous cycle of cosmic renewal, cyclic cosmology offers an intriguing possibility of a universe without a definitive beginning or end, where each cycle builds upon the remnants of its predecessor. In addition to theoretical models, observational cosmology has provided crucial insights into the early universe and its evolution over cosmic time. The discovery of the cosmic microwave background (CMB) radiation in the 20th century offered compelling evidence for the Big Bang theory, presenting a snapshot of the universe when it was merely 380,000 years old. Detailed measurements of the CMB by satellites like the Wilkinson Microwave Anisotropy Probe (WMAP) have enabled scientists to map variations in temperature and density across the early universe with remarkable precision. Moreover, observational cosmology has illuminated the large-scale structure of the universe, revealing the intricate web of galaxies, clusters, and cosmic filaments that stretch across billions of light-years. By studying the distribution of galaxies and measuring their redshifts, astronomers have been able to trace the expansion history of the universe and deduce its age, structure, and ultimate fate. One of the most fascinating discoveries in observational cosmology is the existence of dark energy, a mysterious form of energy that permeates the universe and drives its accelerated expansion. First inferred from supernova observations in the late 1990s, dark energy constitutes about 68% of the total energy density of the universe, making it the dominant component of the cosmic energy budget. The presence of dark energy poses a significant challenge to our current understanding of fundamental physics, as its origin and nature remain poorly understood. Several theories suggest that dark energy may be an expression of vacuum energy predicted by quantum field theory, while others propose modifications to Einstein's general relativity to explain the observed acceleration of the universe. In response to these observational efforts, experimental physicists are actively searching for new particles and interactions that could provide clues about the fundamental nature of dark energy and other cosmic mysteries. Facilities like the Large Hadron Collider (LHC) at CERN aim to probe the frontiers of particle physics by colliding protons at unprecedented energies, potentially uncovering new physics beyond the standard model. Furthermore, advancements in astrophysical instrumentation have revolutionized our understanding of the universe across various frequencies of the electromagnetic spectrum, from radio waves to gamma rays. Observatories such as the Atacama Large Millimeter/Submillimeter Array (ALMA) and the Hubble Space Telescope have transformed our knowledge of star formation, galaxy evolution, and the large-scale distribution of dark matter. Looking ahead, the next generation of observatories, including the James Webb Space Telescope (JWST) and the Square Kilometre Array (SKA), promises to provide new insights into the early universe and its fundamental constituents. These cutting-edge instruments will enable scientists to investigate primordial galaxies, probe the epoch of reionization, and search for signatures of primordial gravitational waves left over from the Big Bang. In conclusion, the quest to understand the origins of the universe represents one of the most profound intellectual challenges of our time. From ancient myths and philosophical inquiries to modern scientific theories and observational discoveries, humanity's exploration of cosmic origins has yielded significant insights into the nature of reality itself. As we continue to push the boundaries of knowledge and exploration, new theoretical frameworks, observational techniques, and experimental advancements will undoubtedly shed light on the fundamental mysteries of existence and our place in the universe. Cyclic cosmology, a theory proposed by the renowned physicist Roger Penrose, who was awarded the Nobel Prize, suggests a universe that expands and contracts infinitely through time. Penrose was intrigued by a remarkable mathematical relationship between the early universe, characterized by extreme density during the Big Bang, and its future state, which is envisioned as a cold, expanded void devoid of matter. This theory posits that these two conditions become mathematically undefined at their extremes. Surprisingly, the complete absence of matter could be the fundamental driver behind the creation of everything we observe today. According to this perspective, the Big Bang emerges from what remains after all matter in the universe has been consumed by black holes, ultimately dispersing into scattered photons within a vast emptiness. This process implies that the universe springs forth from what might be interpreted as nothingness, although this nothingness still represents a form of existence, an empty universe. The intriguing aspect lies in how this identical state can be perceived both as a cold void and as a dense universe, depending on one's viewpoint. The key to understanding this lies in a complex mathematical technique known as conformal transformation, which modifies the size of an object while retaining its shape. Penrose demonstrated that the cold void state and the hot dense state can be interconnected through this scaling transformation, altering their spacetime structures despite their significant differences in size. However, Penrose argues that the concept of time becomes meaningless under these extreme conditions of cyclic cosmology. The sequence of events transitions from an ancient cold state to a youthful hot state. The hot, dense state is thus a product of the preceding cold and empty state. Yet, this causal relationship does not conform to conventional notions of time, as both size and time lose their usual meanings in these extreme states. The cold void state and the hot dense state exist on separate timelines, implying that from the perspective of an observer within its own time frame, the cold empty state would continue indefinitely. In the realm of cyclic cosmology, physics and theory converge, providing theoretical and detailed explanations for the initiation of these cycles. Nonetheless, whether Penrose's ideas gain traction in cosmological advancements, deeper philosophical questions linger about the origins of physical reality itself. Specifically, how did these cycles originate? This inquiry prompts us to consider the justification for the existence of something rather than nothing, which stands as one of the fundamental philosophical questions of our time. There are three potential avenues to explore regarding the origins of these cycles. First, there may be no substantial explanation at all. Second, there could be an endless series of cycles where each cycle represents a different universe, with the initial quantum state of each universe somehow influenced by aspects of its predecessor. Finally, there is the possibility of a single cycle in a recurring universe, where the cycle's beginning is explained by elements of its own conclusion. These possibilities are compelling as they avoid the need for uncaused events and offer a more intricate explanation within the framework of physics. Penrose proposes the idea of an infinite series of cycles influenced by his interpretation of quantum mechanics. In this view, a physical system exists in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose suggests that each cycle is influenced by random quantum events, leading to variations between cycles. This concept opens up intriguing opportunities for experimental physics, as it proposes the potential for identifying subtle traces or irregularities in the leftover radiation from the Big Bang. The quest to understand the origins and nature of the universe has captivated human curiosity and scientific inquiry for centuries. From ancient philosophical theories to modern cosmological models, humanity has persistently sought to unravel the mysteries of existence. In the context of contemporary astrophysics and cosmology, the investigation of cosmic beginnings has led to significant discoveries and compelling theoretical frameworks that challenge our fundamental understanding of time, space, and matter. One of the enduring questions that has intrigued both physicists and cosmologists alike is the nature of the universe before the Big Bang. While the Big Bang theory provides a convincing explanation for the universe's evolution from a hot, dense state to its current expansive form, it leaves unresolved the question of what existed prior to this monumental event, if anything. The notion of a pre-Big Bang epoch raises profound philosophical and scientific implications, pushing the boundaries of our knowledge. Several hypothetical models have been proposed to tackle this question, each offering unique insights and perspectives on the early universe. One such idea is that of the multiverse, which posits the existence of a vast array of universes, each with its own distinct physical properties and fundamental constants. Within the multiverse framework, our universe is merely one among countless others, each arising from different initial conditions and governed by its own set of physical laws. The concept of a multiverse naturally emerges from certain interpretations of quantum mechanics and cosmological expansion theories. According to inflationary cosmology, the rapid and extraordinary expansion of spacetime in the early universe could have resulted in the formation of pocket universes within a broader multiversal landscape. Each pocket universe would possess its unique properties, shaped by random quantum fluctuations.